So it's my pleasure to welcome Nate for a second talk of the semester. He'll talk today about oligomorphic and linearly oligomorphic groups.
Great. Yeah, thanks for having me. So I'm going to talk about oligomorphic groups, which is a class of groups that I had never heard of until 2 years ago, and I'm guessing most of you have not heard of it, except I probably mentioned it in my job talk about a year ago. But it's been, we found some surprising connections to these groups, to representation theory, and it's proven to be like a really fruitful direction. I think, I've been on 7 papers so far about these things, and there's a bunch of others that I wasn't even a part of. So it's been a really fruitful direction to go in. But yeah, I want to kind of explain what these groups are and where they're coming from, and then talk about kind of why I care about them, and maybe a generalization, putting them kind of back in the world of Lie theory or algebraic groups. But let's start with some basics. So this is probably going to be more model theory than we're used to at this seminar, but it happens. Okay, so I want to, as a warm-up, I want to talk about total orders. Okay, so here's a theorem. There is a unique, and I'll be unique up to isomorphism, a unique total order let's write it as A less than such that, well, 1, I want A to be countable. All right. 2, A does not have endpoints. Right, so there's not like a maximum element or a minimum element. There's always something bigger than anything you have or smaller than anything you have. And 3, this is what we say A is dense. And this means that for all, say, A less than C, they're just a B in between them. They're just a B. Suggestively write like an interval. Right, B is greater than A, but less than C. All right, so there's a unique such total order with these 3 properties. So can anyone tell me why such a thing exists?
Rational number.
The rational number. So the rational numbers with the standard order on them have this. So certainly such a total order exists, but maybe the uniqueness is sort of less obvious. Okay. So let's go through a proof of the uniqueness. So suppose I have 2 of these things. So we're going to suppose A, then N. I'm going to use the same symbol for less than for both of them. These are both satisfying this. We want to show that there's an isomorphism between them, that they're really the same. All right. So I'm going to go through a quick proof of this. Should be illustrative. So step 1, I'm going to, unfortunate use of word, I'm going to order them both. By which I mean I'm going to use the fact that they're countable to just put them in bijection with the natural numbers. Okay, so I'm going to order them. A0, A1, A2, dot, 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 B0, B1, B2. But importantly, these are not actually like in increasing order or decreasing order. I'm just using the countability hypothesis, like without actually looking at the. All right. So now, what I'm going to do is I'm just arbitrarily going to send A0 to B0. All right. I'll just take my first thing on the A side and send it to the first thing on the B side. All right, now I'm going to pick B1, and B1 needs to get matched with something, right? We're gonna have a bijection between them. And I want to like map B1 to A1, but I might not be able to, right? Because let's say if B1 is greater than B0, but A1 is less than A0, you can't match them up. But what I can do is I can map B1 to the smallest, or like the first entry in this list that does satisfy it, right? So because there's no maximum or minimum, right? If B1 is greater than B0, there's definitely some A on this list that's greater than A0. And I'm just going to pick the first one on the list that works. Okay. To the AI with I minimum. That preserves the order. Okay. I'm gonna shorthand. And then what I'm going to do is I'm going to sort of repeat this. I'm going to pick the least unmatched a J and send it to the least EK that preserves this. And in particular, if this J is between two things, the B I choose has to be between the corresponding things already chosen. To least EK preserving. Right, and I'm guaranteed to be able to do this because of the density, right? So if maybe I've already used A0 and A1 on these first two steps, but then I'll take some A2, and maybe I'll have to send it to something that's between those two values, but one definitely exists because of this density. Or if it's on either side because of the endpoint condition. It's very much like an ordered version of Schroeder-Bernstein. Yeah, it's definitely has that feel to it. And I just keep doing this. I go back and forth. So I take the least unused B and find an A that's minimal that preserves the structure to match it with. And then I do it on the A side and back and vice versa. And the reason you have to go back and forth like this is because you want it to be bijection. You want to make sure everything gets hit. So if you just do it on the A side or just on the B side, you might miss something. But because we're kind of building this bijection back and forth each time, after every step, we're sort of guaranteed to have at least used, after step n, we've used at least like n over 2 A's and n over 2 of the B's. And we have to have all the kind of smallest ones. I guess maybe n over 4 is what you're guaranteed to have the first n over 4 A's with the first n over. But okay, so we just kind of do this back and forth argument, and that shows it's unique. Any questions about this argument? Because, you know, I really want to show this argument because this is one of the most like important kind of proof arguments in this area. This is called a back and forth argument. Hopefully, obvious reasons. Okay, so a couple things I want to highlight about this argument is if we're in one of these things. Now, suppose I have A1 less than A2.
Just by the way, you're out of the range now of the mark.
Oh, you're very right. So suppose I have A1 less than A2 less than some AK and A1 prime less than A2 prime less than AK prime. So these are going to be you know, two collections of K elements in my my unique total order, which may or may not be Q. Right. The claim is that there exists G in the automorphism group of this structure, right? So this automorphism group is bijections from A to itself, preserving the total order. So there exists a group element in this automorphism group such that G sends this list to this list. G of AI equals AI prime. And the proof of this is actually just that. We just start by creating a function that does this, and then we assign the remaining values one at a time using back and forth. Right, so we're sort of also constructing G inverse, but it's really just, we kind of just start the argument after assigning these K particular values for which we know we're safe because we can fix the order on them. And then we just run the rest of it and we get that. Okay, so this tells us that this automorphism group, not only does it act kind of transitively on the set itself, it actually acts transitively on all like K tuples, ordered K tuples, from K tuples that are in order like this, for all K. So it has this kind of extreme transitivity properties. So, and in particular, if you take kind of any K elements, maybe they're not in order, but you can always send it to any other K elements that are in the same like relative, right? By the exact same argument. So this is going to be the key kind of property of oligomorphic groups. So let me now give the definition that I just kind of said this. So we call them oligomorphic groups, but really it's a sort of group action that is oligomorphic. It is, that chalk is getting too small, I'm going to switch. So a group G acting on a set X acts oligomorphically if X to the n has finitely many orbits all n. Okay, so in this case, if I take endpoints out of Q, maybe they come in some order, maybe a couple of them collide, but the orbit is basically determined by which ones of them are equal to each other, and then what the relative values are, what the like kind of relative positions of those values are, if one is greater than another or not. And it acts kind of transitively on the property by exactly this type of argument. Okay, so that's definition of an oligomorphic group. Okay, I want to give another kind of model theory, classic model theory example. But before I do so, does anyone have any questions about these total orders or total orders?
Where does the name oligomorphic come from?
So it comes from model theorists. They named it, but the reason is, so oligo is the same prefix as oligarchy, and it means few. So, you know, an oligarchy is you're concentrating power among a few elite individuals, whereas, you know, oligomorphic, you have few orbits. Yeah, I don't know.
No, it's okay.
You know, mathematicians getting cute with their naming conventions. Other questions about this? Yeah, so I will say for this property that you can map anything, any k elements to k elements. If you do just identify it with Q, you can just do it piecewise linearly. So it's actually not a very hard theorem once you know that it's Q. But I still wanted to go through this argument, this back and forth way of showing that, because, well, we're gonna want to use it again in a second. Any other questions? Okay, so the next example, I want to discuss is the following. So here's a theorem. I'm going to write it sort of informally first, and then I'll make it a more precise statement. So theorem. So take countably many vertices. So I'm going to construct a graph. So for each pair, flip a coin. And include the edge. If it's heads, and don't include it if it's tails. Okay, so I'm creating a graph at random. This is like the simplest model of a random graph for finitely many vertices. This is what's called the Arish-Radke model. But for infinitely many vertices, I'm just gonna, you know, for every pair, flip a coin, and either include the edge or don't include the edge. And the coin, let's say, is a fixed probability, not 1 or 0. But could be 50-50 if you like. Doesn't have to be. The theorem is that there exists a graph R such that the result I don't know, maybe you may call this graph G. Well, G is R. So there's a unique graph, let's say a unique graph R such that the resulting graph is that one. So you're doing this random process, but you do it infinitely often, and theorem is you always get the same thing. Right. So of course, if we have finitely many vertices, this like couldn't possibly be, right? Like there's a non-zero probability that you just don't include any edges. And there's and that because you just include all the edges. So this is definitely something that is only happening at the sort of infinite level. And this graph is called the Rado graph. That's why I'm calling it RADO. Okay. But this graph is we're going to be able to characterize it. And so really, this is saying it will say that there's a unique graph with such and such properties, and then, well, we'll convince ourselves that a random graph has to have those properties. Okay. So that's the other version of this theorem is so there exists a unique graph R such that, well, I'm going to set it up very similar to my total orders property. So the first one is we need to assume countability. Right, so countably many vertices or edges, both. And two, the sort of graph theoretic substitute for the two properties we had for total orders going to be the following: is that for any finite sets A and B with right, so I have two disjoint finite sets. There exists a vertex in R such that, and I'm not going to write it out, I'm just going to draw you the picture. Here's A, here's B. X connects to everything in A, but nothing in B. Okay. So first of all, do you guys agree that a random infinite graph in this sense should satisfy this property? Maybe. So I guess the point is, for any one vertex, there's some probability that this happens, some non-zero probability that it happens, but then you run that test infinitely many times, right? So even it has a 0.2 chance of percentage of happening. Well, if you run it 30 billion times, it is bound to happen. All right, so that's the property. So there's a unique graph R with these things. And so in fact, I'm not going to dwell on the exists. I mean, you could just argue probabilistically like this. We also have explicit constructions. So there's actually explicit constructions of this graph just on like the natural numbers say. So it's not a purely probabilistic thing, but it's a nice kind of statement of it as this random graph. Okay, but I want to talk about the uniqueness because that's one of the key properties. So why is this unique? So let's do the same proof that we did for the rational numbers and the total orders. All right, so let's prove it's unique. So we're going to suppose we have R prime two graphs. I'll say one S for, so I'm not writing a bunch of primes at this part. So if I have two graphs, R and S, satisfying one and two. Yeah.
So condition 2 is that X.
Yeah, so I have these two sets A and B, and X has to have an edge to everything in A, but nothing in B. So all of the edges over on this side exist, and none of them on this side do. Okay, so suppose I have two graphs satisfying 1 and 2.
You can pick another color.
Yeah, that's
Thank
fair.
you.
This. So step 1, just like last time, I'm gonna order these two because it's countable. I'm gonna use that countability hypothesis. So order them. R0, R1, and S0, S1. Right, and again, this ordering has nothing to do with the graph structure. We're just picking some ordering using the countability hypothesis. All right, so now let's try to do the same trick, and we'll see, it just kind of works. So we're just gonna send A0 to B0.
R0 to X.
Yep. R0 to S0. Then we're going to send S1 to, well, we'd love to just send it to R1, but it might not have the same graph structure, right? So if S1 and S0 are connected by an edge, we have to send S1 to something that is connected to R0. Right, so we're going to send it to Ri with I minimal, such that, and the condition that we want is I'm going to write it like this: S0, S1 is isomorphic to R0, Ri, where this I'm denoting, these are like the subgraph generated by it, the induced subgraph. So just the edges that are between those vertices and ignoring everything else. Right, so we take the minimal I so that either Ri is connected to R0 if these two are connected, or not connected if they're not connected. Okay. And this is going to be guaranteed to exist by this property. So we'll take, A to be R0 and B to be maybe the empty set, or maybe vice versa if they're not connected. Right. And then we're gonna just iterate this process. So now we're gonna take, kind of steps 4 and onwards, we're going to take the least unmatched. So I guess the next step we would take an R to start with, Rj, and send it to Sk with, again, K minimal, and the same induced graph structure on those vertices. Same induced graph structure. Okay, so this one's a little bit harder. So let me sort of draw a picture for you what the general step kind of looks like. So at some point in this process, we'll have matched up some number of things already. So I'll have kind of two partial graphs that are isomorphic to each other. I drew them in a way that's suggested. And now I'm taking my next new vertex, let's say on this side. And this now forms a graph with all of these. I just look at what does it connect to. So it's going to connect to the sum of these vertices, but not to others. Okay? And now what we're going to do is we're going to send it to the least indexed vertex on the other side that matches up in the exact same way. Right? And then we're going to use this property to guarantee the existence of one. So when I want to send this new vertex to something on this side, I say, well, okay, I have my two sets. In this case are A and B. And so I use my property to say there's something that has to connect with everything in A, but nothing in B. And that's a safe thing to match this vertex to. All right. So then we continue this. Again, alternating sides, which one we're matching up. That way you don't miss anything. So we're trying to constrict it bijection. And that gives us a bijection between these two graphs. All right, any questions about this? So this is the Rado graph. It's neat. It's kind of cool. So let me maybe point out some of the nice properties of the Rado graph. So one observation is when we have this graph, this infinite random graph, we can get a random graph on finitely many vertices by randomly just choosing vertices out of this Rado graph and kind of taking the graph they generate.
I get a random set out of an infinite set though.
Carefully. That's how. No, you don't. It's not sort of limiting. But I guess the point of why I was sort of saying that is one thing that sort of suggests is that every finite graph embeds in R. So any finite graph, you can find a copy of it, right? You just look at that number of vertices. It'll be kind of randomly be the right graph with probability, 1/2 to an appropriate power. I guess if the probability is a half. So every graph embeds in R, but infinitely many times. Right, and by embeds, I mean embeds as an induced subgraph. So like not just mapping the edges in, but also mapping the non-edges. So maybe we should look at induced. So this infinite graph, it really sort of sees all finite graphs infinitely many times. But maybe surprisingly is that the automorphism group of this Rado graph, which maybe a priori, it's not obvious that this should have any automorphisms at all, right? It's like a random finite graph will probably not have very many automorphisms. But the automorphism of this Rado graph actually acts transitively on the copies of any fixed graph. Fixed finite graph. So not only do finite graphs embed in this thing all over the place, you can take any two copies of it, map one to the other, and that will extend to an automorphism of the whole thing. Right, and the proof of this is again back and forth. You just start by constructing your function that does what you want it to do on those two subgraphs where there's not a problem, and then you construct the rest of the automorphism one thing at a time, going back and forth, constructing the element of the automorphism and its inverse kind of simultaneously. All right, so that is a much larger group than you might expect for something random like this. And regularly, this is going to be an oligomorphic group. So what this tells us is that if we look at the action of G on the vertices, then if I look at n tuples of vertices, well, okay, there'll be some tuples where maybe two of them collide or something like that, but the general strata is where they're all different. And we look at just like the graph that they form. And this says that, well, we can map it to any other copy of that graph. And then the strata where there are collisions between them, it's just another smaller case of this, maybe with some labels. So this oligomorphic condition that we have finitely many orbits, in this case, is essentially saying for any n, there are finitely many graphs on n vertices. That's the sort of lead term in the number of orbits is just counting graphs. So this is another oligomorphic group. All right. So that was two examples, and they both had this sort of common flavor to it. We constructed these groups as kind of automorphisms of these like universal, very homogeneous objects. And that's not just a coincidence, that's sort of a general fact, that's where these come from. So these are also examples. So the Rado graph, and this universal total order, these are examples of what are called Frise limits. There's several accents on these. I think there's one on the I, maybe also E. Sorry to anyone who knows better. These are examples of Frise limits. And so Frise limits.
Isn't it going to be sort of a fact that like plot R is going to be sort of the same as R because the stabilizer of, I mean, the stabilizer of an element, you know, I mean, I guess the stabilizer of a vertex is going to be somehow just like plot R itself again. So I'm not.
It's a little, it's not quite. So you have, so Rx sort of transitively, right? But if you stabilize a vertex, you're going to now have two orbits, the stuff that connects to it and the stuff that doesn't connect to it. So it's not quite.
In the way that transitively on R, it's not well, I mean,
So this one is actually maybe more easy to describe. So if I stabilize a point, right, then the stabilizer of that point is actually just two copies of the same group. It's like this is, you know, aught Q. I have a stabilizer of a point is aught q cross aught q. You just act on the two like intervals on either side of it. So there's almost a sort of fractally nature to these.
Like the stabilizers are just
Yeah.
much larger than the original.
Exactly. It's a weird property. So like this group is really cool. You can like restrict from G to G cross G, which is not something you could normally do. So let me continue with this. So Frise limit is associated to a theory in the model theory sense of the word theory. So these are associated to certain theories. And I mean this in a like precise model theoretic sense, but I'm not gonna say what that is. But for example, total orders or graphs. Right. So you might think of it as like a set with some structure on it, subject to some rules. That will be a theory in the model theory sense. And what they are these are going to be kind of countable models, meaning what you think, right? They're countable. Then they're going to have two important properties, that they're universal. So universal is going to mean exactly this property, that every finite version of it embeds inside of it. So every finite total order sits inside Q in a total order preserving way, right? I mean, finite total orders are maybe not the most interesting objects, but so universal means contains all finite models of that theory, and then also homogeneous. Which exactly is this property I kept highlighting, that not only do we contain any finite graph or finite total order, but any two copies of it are exchanged by the automorphism. Right? So for any map of finite substructures inside this Frise limit, you can find an automorphism of the whole thing that sends one to the other. That's this homogeneity property. So that's what Frise limits are. That's like the definition of them. When they exist, they're unique by exactly a back and forth argument. And there is Frise's theorem gives a characterization of when a theory will have one, just in terms of the actual models of the theory. So this isn't a model theory class or model theory seminar, so I'm not going to go into the details of it. But it involves kind of looking at how they glue together, and basically saying you can kind of always, you have two substructures that agree on some small part. There's some larger one that like contains the whole union, possibly more than roughly. That's the key condition you need to. Okay, so that's a very rough introduction to Frise theory. Now let me just very briefly kind of say why I care about any of this. Maybe this I won't even really write anything down. We got interested in these because we were trying to construct certain tensor categories. And this property of having finitely many orbits naturally corresponds to a finite dimensionality condition on the morphism spaces in these types of categories we were working with. So that was something we wanted. That was sort of part of the definition of the thing that we were trying to build. And it was exactly this property of having finitely many orbits that we kind of needed to get that. So that's where I was sort of coming from, and how this condition, we thought of it, eventually we stumbled into the model theory literature. We're like, oh, there's actually a class of groups like this, and there's way more examples than we knew about. I basically knew about the infinite symmetric group is oligomorphic. That was that maybe infinite general linear group over a finite field. But yeah, it turns out there are way more, and there's all this literature in kind of the model theory literature about exactly this condition that I was looking for. So that was sort of my original interest, and that's proven to be really fruitful. But now I want to talk about one sort of particular generalization or extension of these ideas, and that's going to be what I call linear oligomorphic groups. But maybe before I go on, does anyone have any questions? Because I know I went through that very fast, but again, algebra seminar, not model theory seminar. Although you wouldn't know today.
But for example, like are the groups ought R and ought Q, are they known to be different groups or are they isomorphic groups? I mean, you could imagine this kind of infinite process that all these groups are really all isomorphic.
They are very different. So yeah, they are different, but it's not so obvious. One thing you can do, for example, is you can measure kind of how, so you have this number of orbits, right? That is finite. You can basically measure how fast that grows. So for let's say subsets of n points in Q, then, well, basically, assuming none of them collide with each other, there are n factorial relative positions that you need, right? Because we have this part for this total order. But whereas if we are counting graphs, there's something like 2 to the n choose 2 graphs. May possibly we have to modify some symmetries, but that's the order of growth. So that's like, growth on the order of like 2 to the n, or like some constant to the n squared, as opposed to n log n, or no, sorry, e to the n log n.
So it's like sounds almost like the only invariant you could get would be like the number of orbits on x to the n.
No, people study the group structure of these things too. They're very different groups. Again, so this Q, monomorphism Q group has this property that sort of the open subgroups, there's a natural topology on these. The open subgroups are stabilizers of points, or maybe things that are that up to finite index. But in this case, they're literally just stabilizers of points. And every open subgroup is just in the form G times G times G times G some number of times. So the Rado graph, it's not that. So there's people study the actual like group structure of these. Are there elements of the group of finite order? So in the Rado graph case, I believe there are, but there aren't any finite order elements in Q. So there's you can actually start doing like group theory questions on these to really distinguish them. And it's kind of a zoo. There's like a lot of examples, and they can have lots of different properties. It's it's not that uniform across all of them.
No, I was just wondering, like, what could you possibly prove about these kinds of groups? That's interesting. Thank you.
The Rado graph, the homomorphism group of the Rado graph is extremely well studied. It is like there's a ton of literature on all sorts of group theoretic questions you can ask about that. Of these, that's probably the most well studied oligomorphic group.
I asked a question on what you said. So you're able to construct these finite tensor categories?
They're not finite. They're big.
Okay, so they're not finite.
They're not finite, but they have finite dimensional Hom space. That's the key property of them. But finiteness is a little too short. So finiteness might be like, representations of a finite group is a finite tensor category for some notion of finiteness. But representations of GLN is an infinite, is still not finite. So yeah, finite would be very strong, but we're allowing
locally small.
it's locally. Yeah, everything is finite, locally small, enriched over finite dimensional vector spaces. Okay, great. So let me very briefly, I guess, talk about this linearly oligomorphic. So I won't have time to say much, but the goal was to kind of marry this framework with some like algebraic groups, Lie groups, stuff. So, right, so these groups are very discrete. They, they really act on, some sort of countable thing. And we wanted kind of a linear version of it. So we want a version that can handle version to include not, include things like, let's say, I'm going to work everything over the complex numbers, or well, over characters of 0, let's say. The orthogonal group for SP to infinity. So these are symmetry groups of things that are very homogeneous, right? So if I think of GL infinity, I'm not going to be too careful about which version of GL infinity I need. But if I just have a countable dimensional vector space over C, that's very homogeneous, right? Any vector is the same as any other vector up to some, and it's going to have kind of the same thing. It's more complicated. It's not the case that you have this oligomorphic condition. So if I have GL infinity acting on C infinity, I don't have finitely many orbits for all powers of it. So for example, if I just have two vectors that are linearly dependent, you have a full parameters worth of orbits given by what the ratio is between them, right? So there's sort of no hope of having actual finitely many orbits. But nevertheless, C infinity is still sort of like the unique countable dimensional vector space over C. So maybe there's some similarities there. Similarly, we could take O infinity or SP. These are going to be, there's like a unique countable dimensional vector space with a non-degenerate symmetric bilinear form. And there's a unique countable dimensional complex vector space with a skew symmetric bilinear form. These are the automorphism groups of them. So we sort of think there should be something there. There should be some analog of Fresnay theory, and that's exactly what we did. We wrote a paper on it. These linearly oligomorphic groups. Maybe let me though, because I'm out of time. Let me say the sort of surprising, interesting, and maybe exciting thing. So these are all very familiar. So we succeeded at defining a notion of linear oligomorphic, a linear Fresnay theory that encompasses these, but it also has new stuff, right? And that's the exciting thing. So let me tell you a new thing, and this is like a new algebraic group, a new Lie group, but infinite dimensional. So there's that. So there exists again a unique countable dimensional let's say complex vector space with a let's say symmetric trilinear form. Right, so kind of like the orthogonal group, but it's now a trilinear form, which is universal and homogeneous. And let me briefly say what that means. So if I look at a finite dimensional vector space with a symmetric trilinear form, well, once your dimension is, I don't remember what it's from, but it's pretty low. There's actually a moduli of it. So there is no longer like over, over for orthogonal groups, there's like one symmetric bilinear form, one non-degenerate one, finitely many up to isomorphism if you include the degenerate ones. But for trilinear forms, no hope of that. You actually have, a moduli of non-isomorphic trilinear forms on any vector space past, dimension 1 or maybe 2. So being universal is a much stronger thing. You now have any finite dimensional vector space equipped with a trilinear form embeds inside this in a form preserving way. And moreover, any two copies of them can be mapped to each other via this automorphism group. All right, so that's recovery. And well, this is just one example. We constructed kind of infinitely many. More or less, you can replace symmetric trilinear forms with any other type of linear, multilinear form. So, you could do symmetric quadrilinear or skew symmetric trilinear maps, but also weird things where you have basically one for every like Schur functor. You have that type of multilinear map, if you like that sort of thing. But yeah, so we have all these examples of weird infinite dimensional homogeneous things. They're kind of universal in a sense, and their automorphism groups seem to be really cool. But that's all we have so far. Sorry, that's it for now.
If you have finite dimensional trilinear form, what would the stabilizer group of that? What would the group that preserved this tend to look like?
So there's one famous example. So in 7 dimensions,
Like G2 or something?
yeah, so G2 is the stabilizer of a generic symmetric trilinear form. Skew symmetric trilinear form in 7 dimensions. So that would be not quite symmetric, but skew symmetric. And that's a sort of anomaly. Often for finite dimensional vector spaces, a general trilinear form will have no symmetry. So it like maybe you have that one kind of very nice case in 7 dimensions, but then you might find ones that have big symmetry groups. So you can certainly, there are examples where even you can imagine kind of defining a trilinear form by taking like a nice bilinear form and then adding on a linear thing, and then you might get the full symmetry group of that bilinear form. So those will have kind of a full O ends worth of symmetry, but a general trilinear form will not be like that, and then we'll have way fewer symmetries.
Yeah, I guess because GLN has dimension like n squared, and so they're like n cubed by trilinear forms, so they don't have to. So you can get away with having no stabilizers where you couldn't with the bilinear form.
That's exactly right, and the situation only gets crazier when you have more, more than trilinear, more than you have. Like I said, you have lots and lots of non-isomorphic trilinear and higher forms, and also their individual symmetry groups might not have any symmetry, but somehow there's a saying there's like a preferred infinite dimensional one that really sees all the finite dimensional stuff and in a like totally homogeneous way. I'll also say this is actually true over any field. We proved this over any field. So there's a unique up isomorphism rational symmetric trilinear form, even for symmetric bilinear forms over rational numbers. That's of course a much more subtle story. Symmetric bilinear forms over rational numbers, there's lots of them, but again, there's a unique countable one which contains them all and in a totally homogeneous way.
So, are you saying So the stabilizers, these are some open subgroups.
Yeah, so for a general oligomorphic group, you can basically just define that to be a topology. You take a basis of your topology. So I said like an oligomorphic group is really a group with an action. And then we have this condition on powers of that action. So, on like k element subsets of your first action. And you can topologize your group by saying stabilizers of, an ordered k tuple of points is open. And that gives you a nice topology on an oligomorphic group. And then kind of you'll have and then talk about continuous actions and continuous representations and everything like that.
Is that a different topology on this group?
Well, it depends what topology on these you want. Like already, I would sort of by default put something like the Zariski topology. But that's already a little subtle to do for infinite dimensional things. But no, I think we want the stabilizers will be actual, the topology for these is more complicated. It's not as nice. You want some sort of mix between like Zariski like topology and oligomorphic topology. And that's not something we've really worked out, but there is a reasonable way to do it, but I don't know exactly what it is.
Sounds like p-adic group topology. Do you know what p-adic groups are?
So p-adic groups are typically not oligomorphic, but we were heavily inspired by p-adic groups and p-adic methods for some of the stuff that we did with these and how we constructed these tensor categories on the actual oligomorphic groups. So maybe not a direct connection, but in terms of kind of methods and some ideas, very much drawing from that world. Yeah.
I have a quick question. Who's we?
Right, good question. So all of this is joint with Andrew Snowden, and there's a paper just about two papers about automorphisms of Q and automorphisms of a circle version of Q as well, where we constructed it. That's also joined with Noah Snyder. But although most of this is classical and only this at the end that's what Andrew's put in, that's new. All the Frise stuff I was talking about for the first 2/3 of this were very, very classical, probably due to Frise. The model theory people. This is whatever, very year one of grad school for model theorists.
Questions for any? Let's think again.
Yeah, thank you.